Welcome students. During this lecture, we shall discuss about longitudinal and transverse modes of a laser cavity. Longitudinal and transverse mode, or rather transverse and longitudinal modes. Now, we have already discussed the properties of a Gaussian beam, and we see that it has a quality of resonating in a single transverse mode. So here we continue that discussion, and we see that different modes have different correspond to different field configurations. That means different field configurations and different frequencies, they are responsible for different transverse or longitudinal modes. Transverse means perpendicular to the direction of propagation, and longitudinal is along the direction of propagation. As we know, the lowest order mode is rather it corresponds to the Gaussian amplitude distribution. Gaussian amplitude distribution, and it does not have any abrupt phase change wavefront across the wavefront of the beam. This is the wavefront, and there is no abrupt phase change. However, the higher order modes have abrupt phase change across the wavefront. Many times we say the word that we are the the function was monotonous, or we have to come out of the monotonous life. So it means a uh, constantness is there. So here a Gaussian beam has a monotonically decreasing amplitude away from the axis. We have already seen how it changes and what is a Gaussian shape and what is a Lorentzian shape. So in Gaussian shape, most of the intensity is limited near to the axis in a symmetrical way, and it varies very slowly along the transverse direction. So it justifies the word monotonous. That means very slowly, not abruptly. And the other modes, they change abruptly. And to obtain a Gaussian pattern, we usually put a circular aperture like this, circular aperture, so that the other modes are filtered out. And how we do that, we shall see shortly. Now, the Gaussian amplitude distribution can be focused to regions of the order of wavelength lambda, and we can obtain enormous intensities out of that. The narrowest transverse dimension, higher order modes for higher losses for higher order modes. Here, the losses are more for higher order modes. Further, we see using the circular aperture, as I told you, loss suffered by the fundamental frequency is lower than the gain. That means the gain is more naturally, so that the laser oscillates in the fundamental mode. And oscillating in a fundamental mode, what is the fundamental mode? Transverse electric mode, TE004. This we have seen from the Lagrange functions also during the discussion of properties of a laser beam. And however, complex structures, this is a very simple structure, and complex structures, they they provide higher loss for other modes. Higher loss for other modes means that apart from fundamental, we have many different modes along the transverse direction, and many types of pattern, many different patterns are possible. So, using complex structures for different applications, we may apply different types of structures to filter out one or the other mode. For example, this we have seen in the theory of diffraction also, Fraunhofer and Fresnel diffraction also, that if the size and shape of the aperture varies, it is responsible for the output intensity, because there is a phase relationship between waves coming from different parts of the wavefront. For example, a wire placed perpendicular to the axis would select the second order TE01 mode. In this figure, you see how a circular aperture causes the shape. Here we have one mirror which is flat and another mirror which has radius of curvature 10 centimeter, and a laser beam is incident. We have a circular aperture over here of the order of diameter 2 millimeter, and the cavity length is 1.25 meter. So the aperture is 2 millimeters only, and we can see that how it expands, how the beam diverges after coming out from the aperture. So this shape, if we plot it, it will give a Gaussian or Lorentzian shape. Now we further our discussion and discuss the what are longitudinal modes. Various longitudinal modes correspond to a transverse mode. That means corresponding to any transverse mode, there are various longitudinal. We may consider the example of modes in, however, the in sound waves are mechanical waves, but here laser is an electromagnetic wave. Being laser means light, and light is an electromagnetic wave. But as far as wave motion is concerned, we there is a parallel between mechanical waves and electromagnetic waves, because diffraction and formation of nodes and standing waves, all these properties are same to much extent, and therefore we see that uh, uh, we have a standing wave pattern in electromagnetic wave when we have reflection from two sides and in the cavity, in the laser cavity. So corresponding to a transverse mode, we have various longitudinal modes. That means transverse is along the direction perpendicular to the that of propagation, and longitudinal is along the. Now we have, in our previous lecture, we found the transverse distribution, rather the longitudinal distribution of modes in a cavity. We obtained this equation, delta nu is equals to c over 2n0 d. This is the frequency interval between various modes. For example, we consider if the length of the cavity is 50 centimeter, refractive index of the medium is 1. That means we may, for a broad uh, range calculation, we may consider n naught is 1. That means the medium is air or vacuum, and longitudinal mode spacing, we calculate c is the velocity of light. So it is the 3 into 10 to the power 8 and 2, and this is n naught is 1 refractive index, and d is 50 centimeter. That means 15 to 10 to the power minus 2 meters. Solving all this, we obtain these many modes. We have 3 into 10 to the power 8 hertz frequency. That means 300 megahertz. That means in the length of a cavity of 50 centimeter, we can assume 1 centimeter is this much, 2 centimeter, 3 centimeter, and 50 centimeter we can have an idea. So within 50 centimeter we have 300 megahertz frequency. Now what about the gain bandwidth? The gain bandwidth, the gain is, if the gain is 5 and the frequency width is 300, we have the gain bandwidth product 5 into 300. So we have the gain bandwidth of 1500 megahertz. For a single transverse mode, we see that it oscillates in about 5 longitudinal modes. And due to so many modes, of course, the coherence length decreases, because coherence is a function of lower number of frequencies, because more frequencies means more confusion to the system. In holography and interferometry, long coherence length is required. In spectroscopy, higher monochromaticity is required. These are two applications, major applications of this concept. So this causes coherence length, and this is due to coherence time, temporal coherence, spatial coherence and temporal coherence. One requires laser to oscillate in a single longitudinal mode along with single transverse mode. Mostly, it is beneficial in most of the applications that the laser may oscillate in a single longitudinal mode along with a single transverse mode, because as I told you that corresponding to a single transverse mode, many longitudinal modes they may exist. Longitudinal mode, we have seen how they uh, they come into being in a rectangular cavity. Now, what are the methods of obtaining? Simple method of obtaining a mode selection, it is by reducing the length of the cavity. Length of the cavity is this. Intermodal spacing becomes larger than the spectral width over which the gain exceeds the loss in the cavity. Intermodal spacing, what is the intermodal spacing? We will shortly see. Example is that delta nu g, it is a frequency interval which may be called bandwidth, and the coherence length is such that the frequency interval is greater than the bandwidth, then the frequency band C over 2 N naught D is greater than the, uh, the guide frequency width, that means the gain spectrum. And you see, by this gain curve, we have a plot between gain. We have already seen what is the gain. Gain is usually defined by the intensity which is obtained in a useful way, and the input frequency, and there is a frequency corresponding to that, and here it is the frequency nu. And mathematically, what we have seen, there may be a number of modes here. In this figure, what happens? The gain is more than the loss. The gain is more than the loss as far as modes are concerned, and this is the threshold. So there are so many modes here, and the intermodal spacing is delta nu. Now, if we reduce the resonator length, you see that this thing is reduced. So LHS increases. LHS increases, and we have C over 2D. It increases. C over 2D, it increases. Again, this is the gain curve, and this is the threshold. We may see that it is the maximum power or intensity, and the half power points, they corresponding to the threshold. So this graph depicts delta nu. When D is reduced, the resonator length is reduced, the bandwidth, uh, the oscillating mode, the frequency interval, that means intermodal spacing of oscillating mode increases. Now, as far as helium neon laser is concerned, we may consider an example. We take the gain bandwidth as 1500 megahertz, and we consider the cavity length less than 10 centimeter for a single longitudinal mode oscillation. We substitute for here C over 2 n naught D, and this is nothing but delta D. So from here we calculate D minimum. D minimum is C over 2 n naught delta mu G. For a single mode oscillation, it can be obtained easily. A single resonant mode must exist at the center of the gain profile. What is the disadvantage? Volume reduces, so P output is small. In a solid state laser, delta nu G is large. What are the techniques of obtaining this thing? We have a Fabry-Perot etalon like this. Here it is one mirror, here it is second mirror, here it is the active medium, and we have Fabry-Perot etalon, that is a rotating type of mirror. It, when it rotates and it makes some angle and reflects the unwanted signal and accepts the acceptable signal. In many applications, a single oscillating frequency is achieved by locking the frequency. So this technique is known as locking the frequency using Fabry-Perot etalon. It is a feedback mechanism. Frequency of the output of the laser is monitored continuously, Any change in the frequency of the laser is fed back to the cavity as an error signal. The feedback signal is used to control the mirror positions of the cavity so as to keep the frequency stable. Very accurate wavelength meters give frequency accurate to of the order of 2 megahertz, and it is the experimental setup. These are two highly reflecting parallel surfaces and it is a rotating mirror. This element introduces losses to all other frequencies instead of the desired one, as we discussed just. Losses of the unwanted signal nu is more than the gain. So this gives a single oscillating frequency. It can be easily shown, and you may see in the book Tyagarajan and that nu p is equals to p c over 2 nt cos theta. Now continuing about the longitudinal modes, we see that the Fabry-Perot etalon, the formula is this: nu p is equals to p, c is the velocity of light, p is an integer, 2 n is the refractive index, t is the thickness of the etalon, and refractive index, the medium between the reflecting planes, theta is the angle made by the wave inside the etalon. So we take the cosine of that angle. The width of each peak depends on the reflectivity of the surface. Higher the reflectivity, sharper the resonance peaks. Naturally, the width of each peak depends on the reflectivity of the surfaces, because that is how we get the intensity, and the rest of the part is filtered out. The frequency separation between two adjacent peaks of transmission is called the free spectral range. Free spectral range. And it is how transmittance is plotted here. Transmittance and the frequency, and these frequencies are filtered out. So it is free spectral range is greater than the spectral width of the gain profile. Fabry-Perot etalon can be fitted in the resonator. If the free spectral range is greater than the spectral width of the gain profile, then Fabry-Perot etalon can be fitted in the resonator. Now, this is the FSR, free spectral range, and if it is greater than the spectral width of the gain profile, gain profile is this, and it is the spectral width, and if it is more than the spectral width, then this etalon can be fitted. Higher the frequency, sharper the resonance peaks. One longitudinal mode of the resonator cavity coincides with the peak transmittance of the etalon. One longitudinal mode of the resonator cavity coincides with the peak transmittance of the etalon. This we see here. The other modes reflected away from the cavity. This we can easily imagine because it is a rotating type of thing. So it reflects the other modes, and for example, we want to select the Gaussian. So when it is parallel to the mirrors, only that one is accepted. The other modes reflected away from the cavity. It depends on the finesse of the etalon. In optics, we see the finesse of the Fabry-Perot etalon that depends on the parameters of the etalon. So here we have the gain spectrum, and gain along with gain spectrum we have the plot of transmittance, and transmittance, you see, it is more than delta nu g. That means intermodal spacing, and due to this, only single mode of oscillation exists. Rest they are filtered out. Here we see that the free spectral range is greater than the spectral width of the gain profile. Spectral width means this thing here, delta nu. So it is more than the value of delta nu. In that case, only single mode of oscillation is possible, and rest they are filtered out. So this completes the longitudinal and transverse mode, and in the next lecture we shall discuss about how mode locking and Q switching is achieved. So this is just one example of how modes are selected. So one method is using a Fabry-Perot etalon. So rest of the methods and what is the concept behind it, we will discuss in the next lecture. Till then, bye. Thank you very much.